Perfect, and it's about time to start. I would like to welcome you all to the second day of the MuniHac 2020. Please be aware that this meeting is being recorded and also streamed live on YouTube. So if you unmute yourself here, you will be heard in YouTube as well. There's a Slack channel. I will post it also now here into the chat so that you have the ability to ask questions in both channels. So here in the Slack chat, here in the Zoom chat and in the Slack chat, the questions will be forwarded by me to Andrew Lelechenko. And yeah, so yeah, that's already time then to introduce him. I already named him. I would like to welcome Andrew Lelechenko. He's a Haskell developer since 5 years with commercial experience in compilers, DSL, and quantitative analysis. He is the maintainer of several key Haskell packages. To name a few, it's bytestring, random, and vector. He has a degree in mathematics, a PhD degree in mathematics. And since 2015, he is working at Barclays for a compiler, domain-specific statistic, strongly typed imperative language to describe exotic derivatives. And yeah, to name them all, developing a sound and robust engine of static evaluation, refactoring, GPU coding generation, and many more things. And today he is giving a talk, as you can see already in his first slide, about polynomials in Haskell. And I'm looking forward for his talk.
Hi, everyone. Um, my name is Andrew, and I'm going to talk about polynomials and how they can be implemented in Haskell. I've been working for about a year on a small library dedicated to polynomial handling, and I would like to present the library itself and its capabilities, and also discuss some insights and some lessons which I have learned during its development. So just to start with, uh, polynomials are simple algebraic construct. Polynomial is either a monomial, which is some coefficient c multiplied by some non-negative power of variable x, or polynomial is a sum of two other polynomials. So we have kind of recursive definition for polynomials in one variable. In technical terms, it's univariate polynomials. So for example, these three expressions are polynomials. 1 divided by x is not a polynomial because power of x is negative here. And these expressions are polynomials as well because they are sums of other smaller polynomials. And polynomials can be added between themselves and multiplied. So technically speaking, they form a ring of polynomials. And I became interested in implementing polynomial library in Haskell. Interesting question is why? Because each time when we implement some mathematical thing in Haskell, we need to check what is the existing prior art in this area. And for vast majority of like linear algebra and algebra in general, differential equations, analysis, calculus, and stuff, there are already Fortran libraries written like half century ago to do this efficiently. So there are probably, and there are certainly efficient Fortran and C libraries to work with polynomials. So why I am bothering myself with writing Haskell native implementation and not just reusing these old proven code, maybe by writing some FFI bindings. And the answer is that these Fortran libraries are mostly monomorphic. and tied to double coefficients. So the only available type for coefficients is double. In some rare cases, it might be integer. Well, the reason is quite simple because people back in 60s were mostly interested in polynomials with double coefficients, and Fortran's story about polymorphism is obviously far from perfect. But these days, I would like to have a polynomial library which is polymorphic in coefficients because, well, because it's 21st century in the first place, and because of my personal applications are not like differential equations, but they're mostly like algebra and cryptography, where coefficients come from discrete fields like think of integer gain, or maybe some modular residues, or maybe some Galois field or stuff. So my reason why I'm working on this library in Haskell is because Haskell's story of polymorphism is probably best in class. However, Haskell track record for performance is a modest one. So the main danger when writing a library of this kind is that we wouldn't be able to achieve anything close to decent performance, because this is not some fancy tree-like structure. Polynomials are usually just an array of coefficients, right? So some old school programming languages will shine evaluating them, and we need to work hard to achieve something comparable in Haskell. So as we discussed, by definition, polynomial is either a monomial or a sum of two polynomials. And this definition can be literally translated into Haskell. Okay, it's just a algebraic data type with two constructors. First constructor is x, and second one is infix constructor plus. No brainer at all. And we can straight away define instance num for polynomials as soon as their coefficients from domain A are numbers as well. So addition is just calling our constructor, and multiplication nicely splits into three cases. Basically, first two cases are just the distributive laws, and the third case is multiplication of monomials. So again, first argument of x is power of monomial, and second argument is a coefficient. So when we multiply two monomials, we add powers and multiply coefficients. And this looks very nice, like we took a definition, we just rewritten it in Haskell without any changes, and we were able to implement numeric instance. But the devil hides in this deriving EQ. We often write deriving EQ absent-mindedly because, okay, dear GHC compiler, could you please derive all this stuff for me? And it happily does. The problem is that as it's defined, addition of polynomials is not even associative, because the order of additions matter, because we'll have different polynomials on top level. And this derived equality is just a structural equality. It will check that polynomials are structurally equivalent, and in this case, they're obviously not. However, for all sensible applications, we would like to have polynomial addition associative. So we need somehow to, either we need to change our equality derivation, or we potentially may need to change our representation of polynomials. So let's look again at the definition. There are some basic blocks, monomials, and there is an associative operation, addition, and there is a neutral element which is represented by a monomial with zero coefficient. It doesn't matter what is power assigned to it. So this means that polynomials are basically monoids over monomials. And we know that lists are free monoids, so we can try and use them to model a non-free monoid. So we will use lists over monomials to represent polynomials. So we define a type for monomial, which is again our x with two fields. Or we define a helper to multiply monomials. It's the same as in the previous slides. And we define a polynomial as a list of monomials, again, deriving EQ automatically, and we can write num instance. So in this case, addition of polynomials is just concatenation of lists of monomials, and multiplication of polynomials is basically repeated addition. So we take first coefficient of first polynomial, multiply it by the second one, then we take second coefficient of xs, multiply it by ys, and so on, and then we fold all our results using addition. This probably looks a bit better, but it still doesn't match our intuition about polynomials. Well, because we managed to fix associativity, but polynomial addition as defined is not commutative. We would expect that x plus y is equal to y plus x, but our definition in which we represent polynomials as lists, it is dependent on the order. Again, what we could do, well, since commutativity means that all rearrangements of our list are equivalent, we can just potentially define EQ instance by hand. We can say that, okay, two polynomials are equal if sorted lists of their monomials are equal. However, it's probably quite expensive check because sort takes a lot of time. And I find that it's very much important to strive keeping structural equality as long as possible. So in any position, if you can design a data type with a structural equality where EQ instance can be just derived, it's probably better to do it this way, unless you need to sacrifice some other characteristics as performance or stuff. So how can we change this? How can we, so if we decide that we cannot modify EQ instance, we would like EQ instance to be derived, how can we change our representation of polynomials to keep up structural equality and to be commutative by addition? So we can define a wrapper, a new type over lists, which will maintain lists sorted together with a smart constructor, which will sort its input and wrap it in new type. And we can write a function which merges two sorted lists efficiently. This is just a normal function from merge sort implementations, for example. So it takes two lists, assuming that they are sorted ones. Yeah, and if one of them is empty, it just returns another one. But if both contain some elements, it looks at their heads, and if x is smaller than y, it emits x and continues merging remaining elements. Otherwise, it emits y and again merges what remains. So if we use this new type sorted instead of plain list inside of polynomial representation, it looks like all is sorted because we have commutative addition and it's also associative, and it looks, if we try and give it some experiments, it will look like it's more or less fine. There are still some things to iron out, because we would also expect that, for example, x plus x is equal to, so the sum of two monomials is equal to just the monomial 2 multiplied by x power 1, and we also expect that 0 multiplied by any monomial is structurally equal to 0. But this can be ironed out in more or less the same fashion. So we define our new type poly as a list of monomials, and we say that addition will call merge function, and merge function is again our plain old friend from merge sort with an addition in the middle. If we see two monomials which have the same power, so k is equal to L, then we check the sum of their coefficients. If sum of their coefficients is 0, then these two monomials under addition, they just canceled out, and we can just proceed with what remains of our sequence, abandoning them two altogether. Or if their sum is not 0, is some value e, then we emit only one monomial instead of two and proceed with merging. And again, definition of multiplication is exactly the same as in previous slides. It just resorts to repeated additions and multiplication of monomials. So this representation is good in that sense that structural equality is restored. We have this, we can just derive EQ. And we also, for example, can derive OR instance, and GHC will do it for us happily. And it means that we can freely store these data, for example, in some map or some set or some other structure, which makes a lot of use of EQ and OR instances, and is written under an assumption that OR and EQ instances are efficient and are not taking some quadratic time or whatever. So I guess this result is a bit expected. I mean, someone could probably guess it from the very beginning, but I think it's important to look at how we can come to this definition of polynomials, going from the very simple recursive mathematical definition of polynomial, and understanding that there is a monoid inside, and then adding some, and then choosing a canonical representative of a class of equivalent polynomials in some way, in our case by sorting and removing monomials with 0 coefficients. So this probably works, but it's still not quite ideal. The problem is that our type for monomials, which is mono A, it takes at least 5 memory words. First of all, it's tag, which basically says that, hi, I am monomial. Then we have a pointer to a power, and we have power stored in additional space. And then we have pointer to a coefficient. And then again, we need to store our coefficient somewhere. It will take at least 1 word, maybe more if it's not an atomic value. It is even worse that a list of monomials which we use to represent a polynomial takes at least 8 words per monomial, because we need to add pointers for a linked list. And if your coefficients, if your type A is a small one, so it's int, word, double, float, then basically it looks like we are spending at least 8 times more memory than we could get away with. And in certain contexts, it's very expensive. It's also quite, it's not like you run out of memory, probably. I don't think anyone will deal with like polynomials with billions of coefficients, at least not from the very beginning. But spending a lot of memory is bad for your garbage collection, and it's bad for your cache, for your CPU cache, so it has a direct effect on performance. We would like to cut these costs. Also, again, this implementation, this list-based implementation, it produced a lot of garbage and tons of thunks, because this, especially it's about this multiplication. There are a lot of nested thunks, and we need to write it very carefully to force everyone, and it still will cause huge pressure on garbage collector. So right thing to do is, well, let's use vectors from vector package. It poses another choice because vectors basically come in two flavors. There are boxed and unboxed ones. And for some data types, we would prefer unboxed vectors if it's like int. And for some others, unboxed vectors are not available at all. So when we design our library, let's be polymorphic by vector flavor. So our data type finally will look like poly with two type parameters. The second one is A for our coefficients, and V stands for our vector type. Is it boxed, unboxed, storable, primitive, whatever. And our polynomial is just a vector of given flavor of tuples. So if A is unboxable, if it's int or double, for example, then usually tuples of word and A are unboxable as well. And we end up with just two vectors, two packed vectors like arrays in C or in Fortran. One is array of powers, and the second one is array of coefficients. So we are as memory effective as we can be, and as memory efficient as Fortran can be. And we will be able to write the same instance, basically num for polynomials. The only addition is that we actually ask our v, so it's missing here, our vb as good flavor of vector to hold pairs of word and A. And the good news are that vectors, using vectors instead of lists, even if it doesn't pose any asymptotic improvement, it makes our arithmetic, our performance like 20, 30 times faster, which is quite good. What is not quite good is that working with mutable vectors in this environment is quite involved. I mean, we were able to fit our implementation of polynomial addition and multiplication with lists on half a slide. But let me show how it looks for vectors. Did it show my editor now?
Nope, it doesn't.
No?
No, it doesn't.
Cool. Cool. So these are in my editor is just implementation. So on the left-hand side, it's implementation of polynomial addition for mutable vectors. And It takes much more space than it used to take on lists. And on the middle part is polynomial multiplication. Not all, it's approximately half of it because it goes up and down from this space. So again,
just briefly, we got a question which I would like to throw you in. Sorry for interrupting. Does the merge function you showed in the previous slide have to change to accommodate vectors? Also directly
yes.
with the note that it may be answered in the future slides.
Yes, basically on the in the left pane of the editor, you can see. Well, we basically cannot use merge function anymore because merge function, as it was presented, it relies on concatenation elements to a list. If we will just literally translate it to vectors, it will be terribly inefficient because adding an element to the head, to the beginning of a vector, just reallocates everything and involves quadratic time and quadratic allocations. So basically, we have to resort to mutable vectors, and this is what is basically happening here. You can find the core part, which is similar to our merge function here. But we basically have two mutable vectors, and very much like you would do it in Fortran or in C, we just have some pointers and we go and we pass both vectors in some in a consistent fashion and change other vector. It's quite involved, unfortunately, but it's a price which we have to pay to achieve decent performance. So basically, the main technical difficulty of this library, which I'm talking about, is that working with mutable vectors is a bit annoying. It requires a lot of low-level manipulations. And for example, multiplication in a constant space without a lot of allocations is even worse, which is in the middle pane here. In the right pane is basically some routines related to division. And again, there are a lot of edge cases, and we need carefully check that we are not out of bounds. And it's quite involved, but it pays off. The benefit is that we get much better performance, which cannot be achieved just by using lists. But it's a main technical difficulty of this library and basically main technical achievement here. I'll switch back to slides.
Yep, perfect. Thank you for the explanation.
So far we were representing polynomials as a list or a vector of pairs of power and coefficient. But there is actually another way to represent polynomials. Like we just chose this list of powers, sorted powers, as a canonical representative of a class of equivalent polynomials. We can actually choose any member of this class as a canonical representative. But it's just a question which choices are good, which choices can be efficiently implemented. So another choice, very popular one, is that we just choose a polynomial of the same degree, but with all monomials for all powers present. So if some monomial is missing, we just assume that it's there, but with a coefficient equal to 0. And since all powers are present, we do not need to store them anymore. We can just assume that we have a list of coefficients, and corresponding monomials have just ascending powers one by one. This would be bad if our polynomial used to have like one monomial of degree 1 million and another one with degree 1 billion, because we will obviously allocate like billion a list of billion elements, but good enough in practice. Most of the time we have polynomials of more or less manageable degree, and we can spare some memory to represent all coefficients of monomials without much trouble. And it saves us from basically having this tuple or mono data type. And what is important for this representation that if we can afford it, it allows us to implement much superior arithmetical algorithms. So we can implement, for example, Karatsuba multiplication algorithm, which, contrary to normal multiplication, has time not like n squared, but n in like 1.6 power, if I recall it correctly. So it's asymptotically beneficial. And on this representation, we can also implement fast Fourier transform, which gives us even faster multiplication in n log n time. So and this is very important in many applications to have good algorithms for multiplication of polynomials. So for example, by implementing these superior algorithms, we achieve a huge speed up in comparison to other libraries for polynomials existing on Hackage. So I've been comparing against polynomial library, and this is multiplication of two polynomials with 100 coefficients, and poly is 50 times faster, and for bigger polynomials speed up grows because we are asymptotically superior, so it's 300 times faster. I wouldn't try it with larger polynomials because their first package would not succeed in reasonable amount of time probably. Okay, so so far we described internals, but we also need some nice way to input and output stuff. So basic thing which we can do, we can just derive, show, and read instances automatically. But if we allow GHC to do it, well, it would look nowhere close to a mathematical expression. If we just derive show, well, it will print some list, and it's not quite easy to understand what is power here, what is the coefficient here, and this poly and poly and brackets are all quite annoying. We would like to have a show instance which prints something close to a mathematical expression. And we can obviously have a handwritten show like this, for example. So we input a polynomial with 3 monomials, and it prints out something quite readable and user-friendly. But what about read instance? It could be possible to write a read instance for this form of representation, but it's probably quite difficult and quite involved. And actually, my insight here is that actually there is no point to support read of some string if we can make this string look just exactly as a normal Haskell expression. So, for example, when I use REPL, I can make some computations, get some printed out by means of show instance answer, and then I can just copy paste it back to input line, because X is actually defined as a pattern synonym in this library, and this string is a completely valid Haskell expression, which is equal to its show instance, basically. And this is much more useful than struggling with read type class. And it gives a very tight loop in REPL. It's good to work with. And this is something which can be, I guess, more widely used in like other libraries and projects. Do not strive to implement read instance. It's enough if your show instance produces a string which is in some sense like can be evaluated, interpreted by Haskell itself. Okay, so we've done this addition, multiplication, subtraction is also fine. What about division? You can obviously divide polynomials. So for example, there is a quaterm function in the Haskell standard library. So if we divide x squared by x, then quotient is x and remainder is 0. If we divide x squared plus 1 by x, then quotient is x and remainder is 1. And if we divide x squared plus 1 by x plus 1, then quotient is x minus 1 as remainder is 2. All good so far. So it looks we should be able to implement division for polynomials as well. But there is a difficulty. If we work with double coefficients, for example, then it makes perfect sense, for example, to divide x by 2. We'll get quotient half of x and remainder is 0. But imagine if we are dealing with this task and our polynomials have coefficients from integer and not from double. What could be a reasonable answer here? Because if we cannot resort to fractional coefficients, we cannot give any sensible quotient here. We could potentially return 0 as quotient and x as remainder, but it looks strange because in no sense we usually expect that the remainder is smaller than divisor, but in no sense x is smaller than 2. So takeaway is that there is no sensible way to define division with remainder for polynomials unless you are dealing with double or rational coefficients. So the only possible implementation of quaterm for polynomials, it requires a fractional constraint. It requires that your coefficients are fractional, and fractional basically means that you can divide coefficients without remainders. And it's quite bad, actually, because first of all, it's very restrictive. Most of the time, for example, in my applications, most of the time I deal with integer here. Another problem is that if I try to model polynomials of several variables by having a poly of poly of poly of a, so this way I model, for example, 3 variables, I wouldn't have, even if my coefficient is fractional, poly of a couldn't be fractional at all. So I wouldn't be able to use quaterm. But there are some good news for people looking for division with a remainder, because often, at least in my applications, division with a remainder is needed to implement Euclidean algorithm to find the greatest common divisor of 2 elements. So normally we implement greatest common divisor GCD by using division with remainder. If we are looking for a GCD of 70 and 25, we can just take remainder of division of 70 by 25, it's 20. Then we take remainder of division 25 by 20, it's 5. And finally, when we divide 20 by 5, there is no remainder. And we know that greatest common divisor of 70 and 25 is 5. It's often important in some algebraic applications to find the GCD of polynomials. But especially when coefficients are integral numbers. But would it be possible? Because one could look at, for example, these two polynomials, 2x² minus 2 and 5x plus 5. And one can prove that the greatest common divisor is x plus 1, because this one is 5 times x plus 1, and this one is 2 multiplied by x minus 1 by x plus 1. But it's unclear how can we compute it, because we cannot use division, we cannot use quadram at all. What would it? It wouldn't make any sense unless we can use fractional coefficient. And good news are that actually we do not need quadram to compute the greatest common divisor. It's a bit counterintuitively, but it's true. The only thing we need is an access to GCD on coefficients. So to implement GCD for polynomials, it's enough to have an access to GCD for coefficients. And this is a very nice property, which means that if we have if we model polynomials of several variables, for example, then to compute GCD of for polynomials of many variables, it's enough to compute GCD for just the field of their coefficients. Idea is that instead of dividing, like we cannot divide 2x² by 5x in any reasonable way unless we can resort to doubles, we can multiply both arguments of GCD to get the same coefficient at the leading term. So in this case, we multiply first argument by 5 and second argument by 2. We get 10x² and 10x. And now we can eliminate this monomial by multiplying the second argument by x. And after elimination, we basically conclude that GCD of these two polynomials is equal to 10x plus 10 up to some coefficient, up to some integral coefficient. And we can define from using GCD on these polynomials and that one. We can use it to compute basically GCD of all coefficients, and we can actually understand that 10 is a redundant factor and actual GCD is just x plus 1. So it's all good, but I would like to have some type class to work with division and the GCD for polynomials. And normally in Haskell, we have an integral type class which features quadram function, and GCD function is implemented in terms of this type class. However, from my point of view, this integral type class is deeply flawed because first of all, we have some very funny superclasses. There is no mathematical reason why integral would require a being real or being enum. It just restricts our choice of a's. So for example, it's no way we can have it for polynomials, because polynomials are not numeratable and are not quite real. Another thing is that integral features two integer function. But if we have two integer function and we also have from integer function coming from num type class, it basically means that the only thing which can be integral, it's either integer or some subring of integer, like smaller part of integer, but nothing which is bigger than integer can be made integral. So for example, polynomials with integer coefficients are obviously bigger than integer itself, so they cannot be integral at all. And even if we change this, even if we remove these superclasses from integral definition, and even if we remove the integer function, it's still not quite good because GCD function requires a being integral. But we already know that for polynomials, there is no need to require an access to quad-rem. We can actually work with more relaxed constraint. So the conclusion is that we need some new type classes. First of all, we need a type class which is basically better integral without superclasses and without two integer. And we also need an intermediate type class for data which allows computation of the greatest common divisor, but not necessarily allows computation of quotient and remainder. And there is a library semirings, and it features these two type classes exactly. So first one is called GCD domain. This notation comes from abstract algebra. So GCD domain is a type class which features GCD, and the Euclidean domain is a subclass of GCD domain which supports quad-rem. And you can have, if your A is Euclidean, you can have your GCD for free, just defined by means of Euclidean algorithm. If A is not Euclidean, well, you have to define GCD by yourself if it's possible. And this fits nicely for polynomials because we have very neat instance. If A is GCD domain, then polynomial of A is also GCD domain. And for Euclidean, we can write an instance which says that if A is fractional, then a polynomial with fractional coefficients is Euclidean. So there is no nice symmetry here. So only some rare polynomials are Euclidean, unfortunately. But normally all of them are GCD domain. So this is so this makes our division look good for polynomials, and this concludes our treatise of arithmetic for polynomials. Just one probably final insight from my work on this package. Its module structure looks like it's shown on the right hand side. You can see that all actual code is under internal subtree. So all these implementations for mutable vectors and stuff, all of them are here. And user-facing modules exposed from Cabal file, which are basically data poly and data poly sparse. They're just basically headers. They just re-export some stuff from internal modules. And I started it as an experiment, but it appears that it's very, very, very convenient. Because if you use user-facing, user-exposed modules to contain actual code, at some point when you need to refactor something, or you move code between modules, or your dense polynomials depends on your sparse polynomials and other way around. For example, you want to write conversion from sparse to dense and back, and you end up with some circular dependency between your modules. And either you have to resort to HS boot files, or you actually have to create these internal modules at this late stage. So it's much better to create internal modules from the very beginning, never show them to users, let them export stuff as they would like it to, and then have user exposed public modules we just collect exported stuff in some sensible fashion and present a nice picture for users and for headers. So All this stuff which I was working on, it's included in package with a short name poly. So we have polynomials, which are polymorphic by coefficients and polymorphic by containers, by flavors of vectors. This package has a lot of features. So we have dense and sparse representations of polynomials, and some extensions like low-rank polynomials, which handle negative powers. Also features cool type-safe polynomials over many variables. Uh, some special polynomial sequences like orthogonal polynomials and stuff. The implementation, as I told, is garbage collector and cache friendly. We use as compact and succinct structures as it's possible. So we are cache friendly, and a good deal of effort is put on reusing memory which was once allocated. So garbage collection is minimal, and this results in pretty good performance. At least amongst Haskell native packages. There is quite a good test coverage, more than 1,000 tests. So I would be happy to hear some feedback and whatever. Feel free to write me on my email, and you can check this package on my GitHub. This talk will be soon available again from my GitHub as well. Thank you very much for attention.
Yeah, thank you very much for your very, very impressive talk. I would like to open up for questions, so please feel free. While hopefully others are typing, my first question is, you already posted your GitHub link. So is it possible to contribute to that package if somebody would like to?
Sure, of course.
You have already a few contributors, or is that work mostly done by your own at the moment?
It's mostly done by my own, but there was, as far as I recall, one or two guys which helped me with to iron out some difficult places.
Mhm. When did you start with your work? I mean, over 1,000 tests, 98% coverage. That looks like a lot of work.
Well, writing tests is
Yeah, but
always
still.
quite terrible. It's probably more or less about a year.
Okay. Wow, that was fast improvement you made. Do you also use that package in your commercial applications, or is it really just a side project apart from the rest?
I use it for my other pet projects, which is like a RESME package, which is designed for number theory
Okay.
and some others.
Okay. As I do not see any questions coming up, this talk was streamed on YouTube and will be there available. No, there I see already a question coming up, so I can directly forward it. How do you quantify how cache friendly a piece of Haskell code is, such as Poly?
Is the question how I can measure cache misses?
Yeah.
Uh,
Yeah, I would say, how do you quantify how cache friendly a piece of Haskell code is? So yeah, I would say, how do you measure the cache friendliness?
I don't think I can measure it directly. It's just a consequence of using as compact data structure as possible. So we are using just continuous allocation of memory here. We don't have any linked lists in this implementation.
Okay, and you also don't have any, I mean, I know it from other software packages where you then can observe directly the cache you're using at the moment. There's something similar possible, probably.
Say it again, please.
Um, I mean, for example, in Java, you can observe the cache while executing the program. Probably that opens the way to compare the cache usage of one library to another, or
It,
did I get the concept wrong?
it would be nice if it was possible in Haskell, but I'm not aware of such kind of tooling. I
Okay.
would be very interested to learn about it, obviously, because it would be a great tool to
Yeah,
measure and improve
I have to admit
performance.
I'm not that deep into Haskell, so it was just an idea that came up from the other languages I know. Um, yeah. Other questions? Just looking around. Um, give me another second. Um, okay. No, I don't see any other questions there. So I would like to thank you again. And I would say you're open for questions if somebody wants to reach you via Telegram or other channels you open here on your last slide.
Absolutely. Thank you for
Perfect.
the opportunity for this
Thanks again for
presentation.
your talk and have a nice weekend.
And you.
Thank you. Bye
Well,
bye.
bye bye.